So here, example 2, we are going to imagine a sphere whose radius r is increasing at a rate of 3 centimeters per second. At what rate is the volume of the sphere increasing when the radius is 10 centimeters? So let's just start off by writing down what the volume of a sphere is. Volume of a sphere is 4/3 pi r cubed. And now we want to know what the rate of change of volume is when the radius is 10 centimeters. So notice here that we're given a rate of change that depends on seconds. So what we should think here is that the radius is a function of time. And the volume is a function of the radius. But because the radius is a function of time, and volume being a function of the radius, this means that implicitly the volume is a function of time as well. It's sort of like a layer deeper. So what we could do here is we don't actually have an expression for this r of t. Now, it is possible to construct one because our rate is a constant rate. It is possible to go ahead and do this, but that's sort of not what we want to do here. Instead, there's two options. Option 1 is to go ahead and just say that v of t, let's say, is equal to 4/3 pi, and then this function that we don't know, r of t cubed. Then if we take the derivative with respect to time, v prime of t, we would have a chain rule going on right here on this term. These are constants. So the 3 would come down, which would cancel with the 3 in the bottom, so we'd have 4 pi inside squared, the inside being r of t, and then we'd have to do the chain rule part where we multiply by the derivative of the inside, which is r prime of t. But here's what we know. We know that the radius is increasing at a constant rate of 3 centimeters per second. So this r prime of t is exactly 3 centimeters per second. And then we're also told that we want to know this rate of change when the radius is 10 centimeters. So we don't actually know what time, we don't know what time corresponds to the radius being 10 centimeters. So although this equation does have time in it, we only know that it implicitly depends on time. We don't have an explicit formula for how it depends on time. So what I could do here is just sort of, since we don't really have any information about time, we could just sort of mod out that time expression. So really quickly, this is 3 and this is 4 pi, so let's make this a 12 pi. So now, if I go ahead and take v prime and say r is 10, we can then just plug that in and get 1200 pi. And this would be centimeters cubed per second. The other thing we can do here is we can say the following. We know that the volume, so that's option 1. Option 2 here would be saying sort of what we did in the very beginning here, what we were thinking. And that is volume is a function of the radius, and the radius is a function of time. Therefore, dv dr is v prime of r, and dr dt is 3 for us, centimeters per second. And I guess if you want to write the units on the volume, this would be centimeters squared, or excuse me, centimeters cubed per centimeter. And then that means that dV dt would have to be dV dr dr dt, multiplying that chain rule through. So then, if we do this entire thing, when the radius is 10 centimeters, then this becomes dV dr, which is r prime. What's r prime? R prime is 4 pi r squared cubic centimeters per centimeter. So this would be 400 pi, if we plug in 10 into this expression, times dr dt, which is 3, which is 1200 pi. So no matter how you think about it, you get the same answer.